I've talked about sketching the graphs for gravitational and electric potentials for the cases when I have either a spherical mass like the Earth or a spherical charge like a glass ball that has electric charges on it. Now let me now take a look at a different geometry. Okay, suppose that this is standing in a field. So this is a grass field, and that's me standing on the grass. Okay, and I'm holding up a ball. I'll use a white ball this time, holding up the ball. Okay, let's say we have a mass m, and suppose that the height of this ball is, okay, suppose it's at height h above the ground. I want to sketch the gravitational potential of this mass. But in the first place, what is the gravitational potential in this case? And we have seen previously a formula for gravitational potential for a spherical mass. But this is, we are talking about the ground here, right? We're talking about gravitational potential from the ground. And we want it in terms of h in this case, where we think of the gravitational field as uniform near the surface of the Earth. So I don't really want to think about the whole Earth this time. Just want to think about the usual, the more familiar gravitational potential energy equals to mgh. So I don't want to use Newton's law of gravitation directly in this case. So using this idea of a gravitational potential, can I think of gravitational potential energy? Can I still think about gravitational potential, and can I plot a graph of that? That's the question I want to think about right now. Okay, let's extend the idea. Recall that gravitational potential is the potential energy per unit mass, right? That's the connection, right, between potential and potential energy. So let me try and write this. So this is potential. Okay. Now, before it gets confusing, let me remind myself that this is PE as in potential energy, and this is just potential. Just potential, which is potential energy for 1 unit mass, maybe like 1 kilogram. Okay. So if potential is the potential energy for a unit mass, that means that I can get it by taking the potential energy and dividing that by mass, as we've done before. Now in this case, because we already know the formula for the potential energy, which is just mgh, I can substitute it into here, mgh over m, and you see that the m and m can cancel. M and M can cancel. So I can actually this time have a formula for gravitational potential, GH, for this geometry, or for this situation, if you like. So this is very different. This is a very different formula from the one we saw in the last session, where we talk about work done from infinity. All right, work done to bring a body from infinity. Remember that if we are talking about mgh, we have a slightly different definition, right? It's still about work done, but this time the reference level is we have a reference level in this case at the ground. So this is the work done to bring the body from the ground. Okay, that's our reference level. Instead of infinity, right, which is used when we talk about spherical mass. So in this case, therefore, we have a different formula, GH, which seems a lot simpler. And I can try to plot a graph of that. Now, if I want to plot a graph, let's see. Let me take this, the vertical axis as the x-axis, and let me take the reference level to be the 0 of the x-axis. So in this case, h would be the same as x. Okay. So let me now try and plot the graph. I want to plot a graph of the potential, gravitational potential phi against x. Okay, so that's 0 there, and the height h would be a certain distance along the x-axis. So I'm just going to say maybe that it is about there. Let's say that's where h is. So how can I now plot the graph of phi? Okay, this part might be a little bit confusing. So phi is equal to gh when the body is at h, but when the body is at some other values of x, I would really use the formula phi equals to gx. Right, so when x is h, then I have this formula. So what I want to sketch now is what phi equals to gx. Now that would probably look quite unfamiliar, right? But let's just remind ourselves of let's just think about phi as y. Now, if you have learned about straight line graphs, you would know about this graph, y equals to mx. If I have a graph of this formula, that would be just a straight line graph. Right, a graph that goes like that, whose gradient is given by m. Okay, so just a straight line. And that's what I would expect here. Okay, because this has the same form as this. The m here is just a constant, like the g here. Phi here is just the y. So I should get a straight line, right? So let me sketch that. I should get a straight line like that. Now what about down here? What about negative x? Okay, things get slightly complicated if I go into negative x, because I have to dig a hole and go into the ground. Okay, if I do that, if I dig a hole and go into the ground, there is the problem that there is this additional complication that the mass of the ground above me would also have a gravitational attraction on me. So it will get slightly more complicated, so I won't go there. Okay, so I'll just take it that I can at least sketch a graph above the ground level, and it would be a straight line, and this is what it would look like. Now let me now go over to the case of electric potential. Now there is actually a corresponding case. Remember that this example of gravitational field near the Earth's surface is an example in which the field is uniform, meaning that at any point around here, the gravitational field strength is the same. So what if I now have so that there is actually a corresponding situation for a uniform electric field. If you remember an earlier video, that's when we have two parallel plates. Okay. Now suppose that I have positive charges on the upper plate and negative charges at the lower plate. Okay, and I have a glass ball here, for example. A glass ball there that has a positive charge inside. So this glass ball is like my white ball that I hold in my hand. If I release this, it will fall. It will be repelled by the positive charges above and attracted by the negative charges below. So there is this force that pulls it down, this electrical force. Okay. So how can I then sketch the electric potential for this example? Now let me start by making an x-axis. Let's say draw a vertical line for the x-axis, and I'll take that to be the 0 of the x-axis. Now, like before, we have to think about the issue of a reference level. It is no longer appropriate here to make use of Coulomb's law directly, because Coulomb's law is meant for point charge or spherical charge. So in this case, we have two parallel plates. So instead, we need to define a new reference level. Instead of infinity, I could define it at one of the plates. Right? I'll just define it at the bottom as the bottom plate, so that it looks like the example with me holding the ball and standing on the field. So if I define this also as my reference level, then remember what potential energy means. Potential energy is the work done to bring body from the reference level, maybe here, to a certain position. So in this case, I'm not going to have mgh. Mgh is for gravitation. In this case, what would I have? What would the potential energy be? If I want to bring this charge from here to there, how much work do I have to do? That would be the potential energy, right? To find the work that I have to do, I must know the force and the displacement, because work is force times displacement. So let me write down what I need to use. Work is equal to force times displacement. I'll call that as the displacement. I've been using D, so I'll just call it D. So what in this case would be the force and the displacement? Okay, if I'm going to, since I take this as the x-axis, I would represent this position or the displacement from the bottom plate to here as x. Okay, so I'm going to just call that my x. So question is, if I lift it up from there to there, what force do I have to use? Right. Okay, for that I need the electric potential, the electric field strength. So let's say the electric field strength is E. So from what we know about electric field strength, we know that it's the force per unit charge, which means that I can find the force if I know the charge Q of this and multiply it by the electric field strength. So therefore this is the force. QE is the force. Right, that's F. And X is the distance that I have to bring from bottom plate to this height. So that's it. That's my formula. QEX. That's my potential energy. Now I really want a formula for the electric potential. So let me write this down. Electric potential. Okay. So I'll call that V for electric potential. And we know that for that electric potential is defined as the work done, or the potential energy, divided by charge. Now since we have the formula for this now, and just substitute this into here, the Q and Q will cancel, and we're left with EX. So once again, it's a simple formula like this. If we think of V as the Y, M, the E there as a constant that doesn't change with X, so we really have just a straight line graph. And now we are ready to sketch it. I want to sketch the electric potential against the displacement X. And that's the formula. Formula is V equals to EX. And it is a straight line as we have seen. That's what it looks like. So it looks the same as the graph for gravitational potential in a uniform field. But there's a slight difference here as well. Let me write this down. Now, as we lift this ball higher and higher until it hits the opposite plate, what happens if I go through the plate? I can either make a small hole and go through, or I can just bring it around and put it on top. What's the potential there above the plate? Well, if you go out of these two plates, if you go outside and above the top plate, the potential would become zero. That's because there's no electric field outside. Basically, once you go out, the plus and the minus would cancel. All right, you can imagine that there would be a field from the minus, and there would be a field from the plus, and they would be in opposite directions. Whereas if you're in between the plates, the force from the positive charge is downwards, force from the negative charge on this ball is also downwards, so they actually add in the same direction. But the moment you move out of the parallel plates, forces from the two plates would act in opposite directions. Right, this would repel, that one would attract. So the field outside of the two parallel plates would be zero, and therefore the moment you go out of the plates, if I let me say that the distance between them is d. Okay, so on the graph, the moment you go out of d, when the moment x increases over d, this graph would drop right down to zero. And likewise, when you go below the bottom plate, the graph would also go to 0. So in this case, we have a straight line, but it only happens between the plates, between x equal to 0 and d. But that's good enough for us, because usually we are just interested in, say, the motion of a charged particle between the plates. I need to make a correction to what I said just now. I've said that when we go beyond d, right? I said that when, or if I bring the charge out of the plate, the potential would drop to 0. Now that's not exactly true. Let me start on this again. So if I start from my reference level, which is here, and bring and increase x, so bring the positive charge up towards the other plate, I have to do work because there is an electric force pulling it downwards. So as I move the positive charge up, I have to do work, which is why the potential increases. Now, but after I have reached the other plate, if I continue to bring it up, either through a small hole or around, right? When I continue to bring it up, as I said just now, there would be no more force, because the plus and the minus on the two plates would produce forces in opposite directions. So as I continue to bring the charge above the upper plate, I don't have to do any more work. But the work that I have done, I will still have had to do work to bring it from the reference level. But it's just that I only have to do work for the part that is in between the two plates. So as I continue to bring it above the upper plate, I don't have to do any more work. Right? It is just that amount which I've used in between the plates. So what this means is that on the graph, I had to do work in between the plate. That's why it increases. But beyond that, I don't have to do additional work. It would just be the work that I have already done in between the plates. So the graph would not increase anymore. It would become constant, meaning just a horizontal line. So that's what the graph should look like. It would not drop to 0 as I said just now. Now, in a similar way, in the negative direction, if I start from the reference level, lower plate, and bring the positive charge downwards, right, to negative x, I don't have to do any work at all, because there's no force below the lower plate, because there will be opposite charges from the minus and the plus charges above. Okay, so as I bring it down from the reference level, don't have to do any work right from the start. So the potential would just stay 0, right, all the way as I move in a negative direction. So it should look like this. So that gives us a more complete picture of the electric potential in and around the parallel plates.